while the entire world remains fixated on 3i Atlas, that enigmatic interstellar wanderer drifting silently through the outer reaches of our solar system, something far more immediate and potentially catastrophic is bearing down on us. Something we've known about for decades, yet somehow managed to push to the back of our collective consciousness. April 13th, 2029. Mark that date in your calendar because it represents the closest encounter between Earth and a massive asteroid in recorded human history. Its name is 99942 Apophis. You might recognize it by its more ominous nickname, the God of Chaos. Named after the ancient Egyptian deity of darkness and destruction, this chunk of rock approximately 340 meters across will pass so close to our planet that it will literally fly beneath some of our communications satellites. We're talking about 30,000 kilometers from Earth's surface. That's closer than the geostationary orbit where your television signals and GPS coordinates originate. To put this in perspective, the International Space Station orbits at roughly 400 kilometers above us. Apophis will pass 75 times farther out than that, but in cosmic terms this is essentially a near miss of unprecedented proportions. An object capable of unleashing the destructive force of hundreds of nuclear weapons, threading the needle between our atmosphere and our satellite infrastructure, like a cosmic bullet grazing our cheek. The official narrative from NASA and the European Space Agency is reassuring. They've stated clearly that Apophis poses no risk of impact in 2029 or for the next century. The calculations have been verified and re-verified. The orbital mechanics are solid. We can all sleep peacefully knowing that disaster has been averted. But here's what they're not telling you in those carefully worded press releases, and here's why I need you to pay attention to every word of this video. The 2029 flyby isn't the end of the story. It's potentially the beginning of a much more dangerous chapter that could unfold over the coming decades. Because what happens when a massive asteroid passes that close to Earth isn't just a spectacular light show for amateur astronomers. It's a gravitational interaction that could fundamentally alter the asteroid's trajectory, its rotation, its surface composition, and ultimately its future path through our solar system. If you're as concerned about this as I am becoming, hit that subscribe button right now, because this is a story that's going to develop in real time over the next few years, and you need to stay informed about what's really happening behind the scenes. Leave a comment telling me where you're watching from and what you think will happen when Apophis makes its closest approach. Are we actually as safe as the agencies claim, or are we witnessing the setup for a future catastrophe that no one wants to discuss openly? The physics of what occurs during such a close encounter are both fascinating and terrifying. When Apophis screams past Earth at its closest approach, our planet's gravitational field will subject the asteroid to what scientists call tidal forces. These are the same forces that create our ocean tides, but applied to a solid rocky body travelling at tremendous velocity. The side of Apophis facing Earth will experience a stronger gravitational pull than the side facing away from us, creating a stretching effect across the asteroid's entire structure. For a solid chunk of iron and nickel, this might not matter much. But recent research suggests that many asteroids, including potentially Apophis, are what scientists euphemistically call rubble piles. These aren't monolithic rocks carved from a single piece of stone. They're loose collections of boulders, smaller rocks and dust, all held together by weak gravitational attraction and perhaps some minor cohesive forces. Picture a giant beanbag chair made of rocks, tumbling through space at incredible speeds. When tidal forces act on this kind of structure, things get interesting in ways that make planetary scientists very nervous. The stress could trigger what researchers delicately term surface resurfacing events. In plain language, we're talking about landslides on a cosmic scale. Material could shift, exposing fresh rock underneath. The asteroid's shape could deform slightly. Its rotation could change. And each of these seemingly minor alterations carries profound implications for its future trajectory. This is where something called the Yarkovsky effect becomes critically important. It sounds like the name of a Russian physicist, which it is, but the phenomenon it describes could determine whether Apophis remains a harmless near miss or evolves into something far more sinister. The effect works like this. Asteroids absorb sunlight on their day side and radiate that energy as heat from their night side. But because the asteroid is rotating, there's a slight delay between heating and cooling. This creates an infinitesimally small thrust, like a weak rocket engine firing continuously in one direction. Under normal circumstances, this force is so tiny that it barely matters. We're talking about accelerations measured in fractions of nanometers per second squared. You could replicate this force by breathing gently on a boulder, but apply that gentle breath for 20 years and you've moved the boulder several kilometers. Apply it for a century and you've displaced it by tens of thousands of kilometers. In the context of asteroid orbits, these minute forces accumulate over decades to create substantial changes in trajectory. Here's the critical point that keeps researchers awake at night. The strength of the Yarkovsky effect depends entirely on the asteroid's surface properties. How quickly does it heat up in sunlight? How efficiently does it radiate that heat back into space? What's the thermal conductivity of the surface material? These parameters determine exactly how much thrust the effect generates, and therefore how much the asteroid's orbit will change over time. If the 2029 flyby alters Apophis's surface properties, even slightly, the Yarkovsky effect changes too. Fresh rock exposed by tidal forces might have different thermal characteristics than the weathered surface that's been exposed to space radiation for millennia. Dust redistribution could change how efficiently the surface absorbs and radiates heat. Even minor shape changes could alter how sunlight strikes different parts of the asteroid at different times in its rotation cycle. The modelling papers that continue to appear in peer-reviewed journals paint a complex picture of these interactions. Researchers have calculated that if just 1% of Apophis's surface experiences material movement during the flyby, it could be enough to measurably alter the asteroid's thermal properties. 1% might sound negligible, but we're talking about potentially millions of tons of material shifting position across thousands of square meters of surface area. What makes this scenario particularly unsettling is the cascade of uncertainties it creates. Before the flyby, we have reasonably precise measurements of Apophis's orbit. We can predict where it will be years or even decades into the future with confidence. But if the encounter changes the asteroid's surface properties, our ability to predict its long-term behavior degrades significantly. The neat orbital projections that extend a century into the future suddenly develop much wider error bars. This is where the concept of gravitational keyholes becomes terrifyingly relevant. When Apophis passes close to Earth, our planet's gravity will deflect its trajectory. Most deflection angles result in the asteroid being nudged onto a harmless orbit that takes it safely away from us. But there exist narrow regions in space, keyholes, where the deflection is precisely calibrated to set up a future collision. Think of it as gravitational billiards. Earth acts as one bumper, deflecting the asteroid at just the right angle to send it careening toward a future collision course. The keyhole for a potential 2036 impact was definitively ruled out by refined observations, but the gravitational landscape surrounding Earth is filled with other potential keyholes for encounters in the 2040s, 2050s, 2060s and beyond. The width of these keyholes varies, but they're typically only a few hundred meters to a few kilometers across. In the vastness of space, that's an incredibly tiny target. But Apophis will be passing through this gravitational terrain at close range, and we're still refining exactly where within that terrain it will travel. Small uncertainties in the asteroid's exact path during the flyby translate to massive uncertainties in where it ends up decades later. Recent research has revealed another troubling possibility. Computer simulations suggest that the tidal forces acting on Apophis during the close approach could potentially alter its rotation state. If the asteroid is currently spinning in a simple, predictable manner, the gravitational interaction with Earth might nudge it into a more complex tumbling motion. This would make the Yarkovsky effect much harder to calculate precisely, because the heated surface would no longer be predictable. A simply rotating asteroid is like a well-thrown football, spinning cleanly around one axis. A tumbling asteroid is like a football thrown by someone who's never played the sport, wobbling chaotically through the air. Predicting the thermal behavior of a tumbling object becomes exponentially more difficult, because you can't easily model which part of the surface faces the sun at any given time. The implications extend far beyond academic curiosity. Our current safety assessments for Apophis depend on models that assume we understand the asteroid's basic physical properties: mass, shape, rotation rate, surface composition, thermal characteristics. These parameters feed into calculations that project the asteroid's future orbit and assess collision probabilities. But if the 2029 flyby changes some of these fundamental properties, our models become obsolete overnight. We would need to start over with new measurements, new assumptions, new calculations, and during the time it takes to rebuild that understanding, Apophis would be following an orbit we no longer fully comprehend. The asteroid that emerges from the gravitational encounter might be subtly but significantly different from the one that went in. This brings us to the missions that will attempt to answer these critical questions. NASA has redirected the OSIRIS-REx spacecraft, now renamed OSIRIS-APEX, to rendezvous with Apophis shortly after the flyby. The spacecraft will spend 18 months mapping the asteroid's post-encounter state, looking for changes, measuring new properties, and providing the data needed to update our long-term risk assessments. The European Space Agency has proposed an even more ambitious mission called Ramses, which would arrive at Apophis before the Earth flyby, observe the asteroid during the close approach, and continue monitoring it afterward. This before, during, after perspective would be invaluable for understanding exactly how the gravitational encounter transforms the asteroid. But these missions require funding and political support that isn't guaranteed. The Ramses mission faces a critical approval decision in late 2025. If it's not approved, we lose the opportunity to observe Apophis in its pre-encounter state, making it much harder to identify what changes during the flyby. The clock is ticking, and the stakes couldn't be higher. We have less than 4 years to make the measurements that will determine whether our current safety assessments are accurate or whether we're sleepwalking toward a threat we haven't properly understood. The god of chaos is approaching, and when it arrives, we need to be ready with instruments capable of answering the questions that matter most. Because if there's one thing the history of asteroid science has taught us, it's that nature doesn't always behave according to our expectations. Every close encounter with an asteroid has revealed surprises, forced us to revise assumptions, opened new questions, even as it answered old ones. Apophis represents the most significant test of our understanding since we began seriously tracking these objects. The difference between a harmless flyby and a future catastrophe could come down to whether a few boulders on the asteroid's surface stay put or shift position during those critical hours when Earth's gravity has Apophis in its grip. Tiny changes with potentially enormous consequences decades down the line. That's the story no one wants to tell you about Apophis, not because it's definitely going to hit us, but because we don't yet know enough to be certain it won't. And uncertainty, when it comes to asteroid impacts, is not something any of us can afford to ignore. The measurements we desperately need aren't just academic exercises. They're the difference between confident predictions and educated guesses about an object that could fundamentally alter human civilization. Right now, our understanding of Apophis relies on observations made from millions of kilometers away, using ground-based telescopes and radar systems that, while sophisticated, can only tell us so much about what this asteroid is really made of. Consider the mass uncertainty alone. We estimate Apophis weighs approximately 27 million tons, but that figure carries error bars that translate into massive uncertainties when you project orbital mechanics decades into the future. The standard method for measuring asteroid mass requires observing its gravitational influence on nearby objects. Since Apophis doesn't have any known moons orbiting around it, we're essentially making educated guesses based on its size and assumed composition. This is where spacecraft missions become absolutely critical. When a probe flies close to an asteroid and measures how its own trajectory gets perturbed by the asteroid's gravity, you can calculate mass with extraordinary precision. It's the difference between saying something weighs approximately 27 million tons and knowing it weighs exactly 26.8 million tons. That level of precision matters enormously when you're trying to predict where something will be in 50 years. The rotation question presents another layer of complexity that could completely upend our current safety assessments. Ground-based observations suggest Apophis spins with a period of roughly 30.4 hours, rotating around a single axis like a well-balanced top. But light curve data from Earth-based telescopes can be deceptive. An asteroid tumbling chaotically through space can sometimes produce brightness variations that look remarkably similar to simple rotation. If Apophis is actually tumbling rather than spinning simply, every thermal model we've built becomes suspect. The Yarkovsky effect depends critically on which parts of the surface face the sun at which times. For a simply rotating object, this is predictable. For a tumbling object, it becomes a nightmare of complex calculations where small errors compound rapidly over time. The surface composition mystery runs even deeper. Spectroscopic analysis from Earth suggests Apophis belongs to a class of asteroids called LL chondrites. primitive rocky material left over from the early solar system, but surface properties can vary dramatically across a single asteroid. Some regions might be covered in fine dust that acts like thermal insulation. Other areas might expose solid bedrock that conducts heat efficiently. These variations directly control how the Yarkovsky effect operates in different regions. What's particularly troubling is that we won't know which scenario we're dealing with until spacecraft actually visit Apophis and map its surface in detail. The thermal infrared imaging needed to understand these properties requires getting close enough to resolve features just meters across. Ground-based telescopes simply can't provide that resolution for an object hundreds of millions of kilometers away. The structural integrity question might be the most consequential of all. Laboratory experiments on meteorite samples have revealed just how fragile these materials can be. Take a piece of carbonaceous chondrite, a primitive meteorite type that likely represents asteroid composition, and apply modest stress. Watch it crumble like compressed dirt. The material has virtually no tensile strength, held together primarily by compression and friction. If Apophis consists of this kind of weakly bound material, the tidal forces during the 2029 flyby aren't just theoretical concerns. They become potential triggers for substantial structural changes. Picture a massive beanbag chair being squeezed and stretched by invisible hands. The beans inside are going to move, settling into new configurations, potentially exposing different materials at the surface. Recent modelling efforts have attempted to quantify these possibilities. Researchers have built computer simulations of rubble pile asteroids with various internal properties, then subjected them to the tidal stresses Apophis will experience. The results show that even conservative assumptions about material strength allow for measurable surface changes during the flyby. One particularly unsettling scenario involves what scientists call rotational breakup. If the tidal interaction spins Apophis faster, increases its rotation rate beyond a critical threshold, centrifugal, forces could overcome the weak gravity holding the asteroid together. Material could start flying off the equator, or in extreme cases the entire object could split along structural weaknesses. This has actually happened to other asteroids. Astronomers have caught objects in the act of breaking apart, pieces slowly drifting away from the main body like a flower losing its petals in slow motion. The mechanisms aren't fully understood, but they probably involve spin-up from thermal effects or gravitational interactions. For Apophis, the question becomes whether the torque applied by Earth's gravity during the close pass is strong enough to accelerate the asteroid's rotation significantly. Preliminary calculations suggest it probably isn't, that the effect is too weak. But those calculations assume we know Apophis's current rotation rate and internal mass distribution accurately. The uncertainty propagation here becomes genuinely frightening when you think about it systematically. Small errors in measuring the asteroid's current state get amplified by the complex physics of the flyby interaction, which then get further amplified by decades of orbital evolution under forces we might not be modelling correctly. It's like trying to predict exactly where a pinball will end up after bouncing through a complex machine. You need to know the initial velocity precisely, understand exactly how each bumper will deflect the ball, and account for friction and other subtle forces throughout the entire journey. Miss any of these factors, and your prediction becomes worthless. The spacecraft missions designed to address these uncertainties face their own challenges and limitations. OSIRIS-APEX will arrive at Apophis approximately 1 month after the Earth flyby, providing detailed post-encounter observations but missing the critical before and during measurements. It's like arriving at a crime scene after the fact, trying to piece together what happened from the evidence left behind. The proposed Ramses mission would fill this gap by observing Apophis before, during, and after the close approach. But the mission requires approval from European Space Agency member states, and that decision hinges on political and budgetary considerations that extend far beyond pure science. Space missions compete for limited resources against other priorities, and politicians don't always appreciate the long-term implications of failing to fund critical observations. Meanwhile, ground-based observation campaigns are being planned with unprecedented intensity. Every major radar facility and optical telescope that can track Apophis will be pointed at it during the months surrounding the flyby. Amateur astronomers worldwide are preparing to contribute observations. The asteroid will be under more scrutiny than any object in human history. But even this massive observational effort has limitations. Ground-based instruments can track position and brightness changes, but they can't resolve surface details or measure thermal properties with the precision needed to fully characterize what happens during the encounter. They can tell us that something changed, but not necessarily what changed, or by how much. The data analysis challenges are equally daunting. The observations will generate terabytes of information that need to be processed, cross-correlated, and interpreted by teams of researchers working around the clock. Pattern recognition algorithms and machine learning systems will help sift through the data looking for subtle signals that might indicate surface changes or orbital perturbations. Yet artificial intelligence introduces its own uncertainties into the equation. Neural networks trained on simulated data might miss patterns that don't exist in their training sets, or they might identify spurious correlations that lead researchers down incorrect paths. The responsible use of these tools requires constant validation against known physics and cross-checking between multiple independent analysis techniques. The communication challenges facing space agencies during this period deserve serious attention as well. How do you explain to the public that you're reasonably confident in the asteroid's safety, while simultaneously mounting the most intensive observation campaign in history? How do you balance scientific honesty about remaining uncertainties against the need to prevent unnecessary panic? The messaging has already begun shifting subtly. Official statements emphasize that continued observations are needed to refine our understanding and reduce uncertainties, rather than acknowledging that fundamental questions about Apophis's behavior remain unanswered. This careful language serves important purposes, but it also means the public isn't getting the full picture of what's at stake. International cooperation becomes critical not just for the science, but for the response if the post-flyby data reveals something unexpected. Planetary defense isn't a problem any single nation can solve alone. It requires coordinated observation networks, shared data analysis resources, and potentially joint missions to deflect threatening objects. The United Nations framework for planetary defense provides a structure for this cooperation, but it's never been tested under the pressure of a real evolving threat. The bureaucratic challenges of coordinating responses between agencies with different priorities, different budgets, and different political constraints could prove as difficult as the technical challenges of actually deflecting an asteroid. What happens if observations after April 13, 2029 reveal that our models were wrong? What if the asteroid's orbit changes more than predicted, or its rotation state becomes chaotic, or surface changes alter the Yarkovsky effect in ways we didn't anticipate? The answer is that we start over with new data, new models, and potentially new timelines for when action might be needed. This is why the next few years represent such a critical window. Every measurement we make before the flyby, every parameter we constrain, every uncertainty we reduce shrinks the probability cloud of future positions. But it also means that any measurement we fail to make, any opportunity we miss, could leave us blind to changes that matter enormously for long-term safety. The god of chaos approaches whether we're ready or not, and our readiness depends not just on the sophisticated technology we've developed for tracking asteroids, but on our wisdom in using that technology effectively, our commitment to making the observations that matter most, and our courage to acknowledge what we don't yet know about one of the most consequential encounters in human history. In human history. The timeline for decisive action grows shorter with each passing day, yet the public remains largely unaware of the mounting evidence that suggests our current approach may be fundamentally inadequate. While space agencies maintain their reassuring public stance, internal documents and research papers tell a different story entirely. Consider what happened during the initial discovery phase of Apophis back in 2004. When astronomers at Kitt Peak first spotted this object, preliminary calculations suggested a terrifying 2.7% chance of impact in 2029. That might sound small, but in asteroid risk assessment terms, it represented Russian roulette odds for our entire civilization. The probability calculations that followed revealed just how razor-thin our margin for error really is. As more observations accumulated over the following months, that initial impact probability dropped steadily, first to 1 in 45, then to essentially 0 as the orbit became more precisely defined. But here's what should keep you awake at night. Those probability reductions came from better measurements of where Apophis is now, not from any fundamental change in the physics of what could happen during the flyby. The gravitational keyhole concept that emerged from that early analysis remains one of the most chilling aspects of this entire scenario. Picture Earth's gravitational field as a complex landscape of hills and valleys extending far into space. As Apophis approaches, it will navigate through this invisible terrain, with our planet's gravity bending its trajectory based on the exact path it follows. Most trajectories through this gravitational landscape result in safe deflections. The asteroid gets nudged onto a different orbit and continues harmlessly on its way. But scattered throughout this landscape are narrow corridors, keyholes, where the deflection angle is precisely calibrated to set up a future collision. These keyholes are typically only a few hundred meters wide, but if Apophis passes through one of them, it gets aimed like a guided missile toward a future impact. The 2036 keyhole was ruled out through refined observations, but that was just one potential danger zone among many. The gravitational landscape surrounding Earth contains keyholes for potential encounters in the 2040s, 2050s, 2060s, and extending decades into the future. We haven't mapped all of them because doing so requires knowing Apophis's trajectory with impossible precision. What makes this situation particularly precarious is how small changes during the flyby could nudge Apophis toward one of these unmapped keyholes. Remember that material movement we discussed earlier? If tidal forces cause even minor surface changes, altering the asteroid's thermal properties, and therefore its response to the Yarkovsky effect, the long-term orbital evolution becomes unpredictable. The Monte Carlo simulations that researchers use to assess these risks work by running thousands of possible scenarios, varying input parameters within their uncertainty ranges to see where things might end up. Current simulations show most outcomes are safe, with Apophis flying by harmlessly and never returning as a significant threat. But those statistical tails of the distribution, the low probability scenarios where things go differently, they're still there. And here's the truly unsettling part. The width of those probability distributions depends critically on how well we understand the parameters that control Apophis's behavior. If post-flyby observations reveal that our models had significant blind spots, those probability clouds expand dramatically. Suddenly scenarios that looked safely impossible start showing up as low probability but non-zero possibilities. The research community has developed increasingly sophisticated tools for modeling these interactions, but each advancement reveals new layers of complexity. Recent papers have explored how different internal structures affect tidal response, how various surface compositions influence thermal properties, how rotation state changes propagate through decades of orbital evolution. The mathematics involved are staggering in their complexity, yet they still rest on assumptions about physical properties we haven't directly measured. This is where the mission approval timeline becomes absolutely critical. The European Space Agency's Ramses mission faces its make-or-break moment at the Ministerial Council meeting in November 2025. If approved, the spacecraft would launch in 2028, arriving at Apophis in early 2029 with enough time to establish baseline measurements before the Earth encounter. Without those pre-flyby measurements, we're essentially flying blind into the most consequential asteroid encounter in human history. We'll have OSIRIS-APEX arriving after the fact to document whatever changes occurred, but missing the critical before and after comparison that would tell us definitively what the flyby accomplished. The political dynamics surrounding mission approval deserve scrutiny because they reveal how institutional priorities can clash with scientific necessity. Space missions require substantial financial commitments that compete against other pressing needs. Politicians making funding decisions don't always grasp the long-term implications of failing to make critical measurements during narrow windows of opportunity. Meanwhile, the broader space weather environment adds another layer of complexity that mission planners must navigate. Solar activity follows an 11-year cycle, and 2029 falls during a period when coronal mass ejections and geomagnetic storms remain possible. These space weather events can disrupt the very observation networks we'll depend on for tracking Apophis with maximum precision. Imagine the nightmare scenario. April 13th, 2029 arrives with every telescope and radar system on Earth focused on Apophis, attempting to measure its post-flyby trajectory with unprecedented accuracy. And on that same day, the Sun launches a massive solar storm directly toward Earth, scrambling communications, degrading GPS signals, and forcing sensitive instruments offline just when we need them most. The probability of such a coincidence is low, but the consequences would be catastrophic for our understanding of what the flyby accomplished. We might miss detecting subtle orbital changes that only become apparent through precise position measurements over the days and weeks following the encounter. This brings us to the broader question of systemic resilience in our planetary defense infrastructure. Our ability to track asteroids and model their behavior depends on a complex network of ground-based facilities, space-based assets, communication systems, and data processing centers. Each component has its own vulnerabilities, and cascading failures could blind us to developing threats at precisely the wrong moments. The satellite infrastructure that Apophis will pass through represents another potential complication that receives insufficient attention. The geostationary belt where many communication and weather satellites operate is a precisely choreographed dance of spacecraft, maintaining exact positions above Earth's equator. While Apophis is too small and fast-moving to significantly perturb satellite orbits gravitationally, the operational disruption caused by tracking such an unprecedented close pass could lead to human errors in satellite management. A collision between satellites in geostationary orbit creates debris that persists indefinitely, potentially triggering a cascade effect known as Kessler syndrome, where each collision generates more debris, leading to more collisions until entire regions of space become unusable. Apophis won't directly cause this, but the distraction and stress on satellite operators during the flyby period could increase the risk of operational mistakes. The data processing and analysis challenges facing researchers in 2029 will be unlike anything attempted before in planetary science. Terabytes of observations from dozens of facilities worldwide will need to be integrated, cross-correlated, and interpreted within days or weeks of the encounter. The computational infrastructure required for this effort must be planned and tested well in advance. Artificial intelligence systems will play crucial roles in sifting through this data deluge, identifying subtle patterns that might indicate surface changes or orbital perturbations. But machine learning algorithms trained on simulated data might miss real-world phenomena that weren't included in their training sets, or they might identify spurious correlations that lead researchers down incorrect analytical paths. The human expertise required to interpret these results and make sound judgments under pressure represents another potential bottleneck. The community of researchers with deep experience in asteroid dynamics and close encounter physics is relatively small. If key experts are unavailable during the critical analysis period, or if institutional knowledge isn't properly documented and shared, crucial insights might be missed. International coordination becomes essential not just for the scientific aspects of the observation campaign, but for the response if unexpected results emerge. The United Nations framework for planetary defense provides a structure for cooperation, but it's never been tested under the pressure of a real evolving threat scenario. Different space agencies operate under different political constraints, budget cycles, and institutional cultures. Achieving true coordination requires not just technical compatibility between observing systems, but also diplomatic finesse in managing competing national interests and priorities. The communication challenge facing agencies during this period cannot be overstated. How do you maintain public confidence while acknowledging genuine uncertainties? How do you explain that mounting the most intensive asteroid observation campaign in history is a prudent precaution rather than a sign of imminent danger? The careful language already appearing in official statements reveals this tension. Terms like refining our understanding and reducing uncertainties serve as euphemisms for acknowledging that fundamental questions about Apophis's behavior remain unanswered. This diplomatic phrasing serves important purposes in preventing panic, but it also means the public isn't receiving complete information about what's truly at stake. The next 18 months represent a critical decision point for humanity's preparedness. Mission approvals must be secured, observation campaigns must be planned and resourced, international cooperation agreements must be finalized, data processing infrastructure must be prepared and tested, and all of this must happen while maintaining public confidence and political support for the substantial investments required. The consequences of inadequate preparation extend far beyond the scientific community. If post-flyby observations reveal that our safety assessments were overly optimistic, we'll need response options ready for implementation. Asteroid deflection missions require years of planning and development. By the time we know whether such missions are necessary, it might already be too late to mount an effective response. This is the hidden story behind Apophis that space agencies prefer not to discuss publicly. Not because impact is inevitable, but because the margin between safety and catastrophe depends on measurements we haven't made yet, models we haven't fully validated, and preparations we're still struggling to complete. The god of chaos approaches with mathematical certainty. Whether we're ready to understand what its passage truly means for our future remains an open question with less than 4 years left to find the answer. Every month of delay in mission approvals, every budget cut to observation programs, every failure to coordinate international response capabilities narrows our options and increases the risk that we'll face the future unprepared. While the world watches distant interstellar visitors that pose no threat to our survival, the real test of human civilization's maturity approaches from much closer to home, and we're rapidly running out of time to prove we're ready for it. The institutional memory of how these close encounters unfold reveals patterns that should deeply concern anyone paying attention to the details. When Apophis was first catalogued in 2004, the initial orbital calculations triggered what can only be described as controlled panic within the planetary defense community. The asteroid briefly achieved a Level 4 rating on the Torino Impact Hazard Scale, a classification that had never been assigned to any object before. Behind closed doors, emergency meetings convened at NASA, the European Space Agency, and observatories worldwide. Researchers worked around the clock to gather additional observations, refine the trajectory calculations, and determine whether humanity was facing an extinction-level event in just 25 years. The public remained largely unaware of these frantic efforts, but the scientific community understood they were potentially staring at the end of civilization as we know it. Those additional observations gradually reduced the impact probability, but they also revealed something that continues to haunt trajectory specialists today. The margin between a safe passage and a catastrophic collision was measured in hundreds of meters. If Apophis had been just slightly closer to Earth during its previous orbital passages, if solar radiation pressure had nudged it just a fraction differently over the decades, if any of a dozen tiny factors had varied by the smallest amounts, we would be facing certain impact rather than probable safety. This razor-thin margin exposes the fundamental fragility underlying all of our safety calculations. We're not dealing with comfortable buffers measured in millions of kilometers. We're walking a tightrope where the difference between survival and annihilation can be smaller than the length of a few city blocks projected across interplanetary space. The modelling studies that emerged from this early scare revealed the true complexity of gravitational keyhole dynamics. Researchers discovered that the gravitational landscape surrounding Earth during close asteroid passages resembles a Swiss cheese of potential dangers. Safe trajectories dominate the picture, but scattered throughout are these narrow channels where precise deflection angles set up future collisions with mathematical certainty. What makes these keyholes particularly insidious is their dependence on factors we can barely measure from Earth-based observations. The exact timing of when Apophis reaches its closest approach point matters enormously. A difference of just minutes in the encounter timing translates to different gravitational deflection angles, potentially steering the asteroid toward or away from future collision courses. The rotation state of the asteroid during the flyby adds another layer of complexity that current models struggle to address adequately. If Apophis is spinning in a simple, predictable manner, the tidal forces from Earth will act uniformly across its structure. But if the asteroid has any wobble or tumbling motion, the gravitational interaction becomes chaotic and much harder to predict. Recent advances in radar astronomy have provided hints that Apophis might indeed have complex rotation dynamics. The reflected signals show subtle variations that could indicate either surface features or irregular spin characteristics. Unfortunately, distinguishing between these possibilities requires resolution that exceeds the capabilities of even our most powerful ground-based systems. The thermal modelling challenges become exponentially more difficult when you consider how surface properties might change during the encounter itself. Laboratory experiments on meteorite samples have demonstrated that these materials can undergo phase transitions under relatively modest stress conditions. Heating, compression, or structural rearrangement can alter thermal conductivity, surface roughness, and reflectivity in ways that fundamentally change how the Yarkovsky effect operates. If tidal forces during the flyby trigger any of these phase transitions, even on a small scale, the long-term orbital predictions become unreliable. We might emerge from the encounter with an asteroid that behaves thermally like a completely different object than the one we've been tracking for 2 decades. The dust ejection possibility represents another wildcard that could completely reshape the risk assessment. Some asteroids, particularly those with loosely consolidated surfaces, can shed material when subjected to stress or heating. This isn't necessarily catastrophic breakup, but rather a more subtle process where fine particles get lifted away from the surface by various mechanisms, Even minimal dust loss during the Apophis flyby could create measurable changes in mass distribution, rotation dynamics, and surface composition. The ejected material might form a temporary debris cloud that alters how sunlight interacts with the main body. These effects cascade through the physics in ways that make long-term predictions increasingly uncertain. The spacecraft missions designed to characterize these phenomena face technological challenges that push the boundaries of current capabilities. OSIRIS-APEX will need to operate in an environment where solar radiation, thermal cycling, and potential debris from surface changes could damage sensitive instruments. The mission planners are essentially designing a spacecraft to study an object that might be actively transforming during the observation period. The proposed Ramses mission confronts even greater technical hurdles. Observing Apophis during the actual flyby requires the spacecraft to maintain precise positioning, while the asteroid experiences rapid changes in gravitational environment, solar illumination, and potentially structural configuration. It's like trying to photograph a race car while riding in another vehicle travelling at highway speeds through a construction zone. The data transmission challenges alone could prove overwhelming. High-resolution imaging of surface changes, thermal mapping of temperature variations, and precise tracking of rotation dynamics will generate data volumes that exceed the capacity of current deep space communication networks. Mission designers must balance scientific completeness against the practical limitations of getting information back to Earth in usable timeframes. Ground-based observation campaigns face their own constellation of difficulties that receive insufficient attention in public discussions. The asteroid will be visible primarily from certain geographic regions during critical phases of the encounter. Political instability, weather conditions, or equipment failures at key observatory sites could create gaps in the observational record precisely when continuous monitoring is most essential. The international coordination required to maintain global coverage involves dozens of facilities operating under different institutional frameworks, funding structures, and technical standards. Achieving true data compatibility across this diverse network requires years of advanced planning and standardization efforts that are still incomplete. Radio frequency interference from the growing constellation of communication satellites poses another emerging threat to the precision observations needed during the flyby period. The electromagnetic environment around Earth has become increasingly cluttered, making it harder to detect the faint radar echoes that provide crucial information about asteroid rotation and surface properties. The timing of the Apophis encounter, relative to solar activity cycles, introduces additional complications that mission planners must navigate carefully. Solar storms can disrupt the ionosphere in ways that degrade radar performance, interfere with satellite communications, and force sensitive instruments into protective modes precisely when maximum sensitivity is required. The computational challenges of processing and analyzing the observational data will strain the resources of even the most advanced research institutions. Real-time orbital determination requires massive computational power to integrate the complex gravitational dynamics, account for various perturbative forces, and propagate uncertainties through decades of future evolution. Machine learning algorithms offer potential solutions for managing these computational demands, but they introduce new categories of risk. Neural networks trained on synthetic data might miss real-world phenomena that weren't included in their training scenarios. The black box nature of these systems makes it difficult to understand when they might be producing unreliable results. The human expertise required to interpret complex dynamical data and make sound judgments under time pressure represents a potential bottleneck that receives little public attention. The community of researchers with deep experience in asteroid encounter dynamics is relatively small and concentrated at a few institutions worldwide. If key personnel are unavailable during the critical analysis period, or if institutional knowledge hasn't been properly documented and transferred, crucial insights about Apophis's post-flyby behavior might be overlooked or misinterpreted. The consequences of analytical errors during this period could persist for decades. The policy implications of various observational outcomes remain largely unaddressed by current planetary defense frameworks. What happens if measurements reveal that impact probabilities are higher than previously calculated? What mechanisms exist for rapidly implementing deflection missions if they become necessary? How are international resources mobilized and coordinated under emergency conditions? The United Nations Framework for Planetary Defense provides theoretical answers to some of these questions, but the practical implementation details remain untested. Bureaucratic processes that work adequately for routine scientific cooperation might prove inadequate for managing a genuine planetary emergency with tight time constraints. The financial implications of various response scenarios could prove as challenging as the technical aspects. Asteroid deflection missions require substantial international investment and coordination over periods that span multiple political and budget cycles. Maintaining sustained commitment to expensive programs based on probabilistic rather than certain threats test the limits of democratic decision-making processes. Public communication strategies during and after the flyby will require unprecedented sophistication in explaining complex scientific uncertainties without causing unnecessary alarm or complacency. The challenge lies in acknowledging genuine risks while maintaining confidence in our scientific capabilities and institutional preparedness. The media coverage of the event will likely focus on the spectacular visual aspects of the close approach, while missing the subtle measurements that actually determine long-term safety. Correcting misunderstandings and maintaining accurate public discourse about evolving risk assessments requires coordination between scientific institutions and communication professionals. The psychological impact on both researchers and the general public of living with evolving but uncertain threats deserves consideration in planning response strategies. Unlike acute emergencies that demand immediate action, potential asteroid threats can persist as background concerns for decades, affecting resource allocation decisions and social priorities in subtle but significant ways. The technological legacy of the Apophis encounter will extend far beyond the immediate scientific results. The observational techniques, computational methods, and international coordination mechanisms developed for this event will establish precedents and capabilities for managing future asteroid threats that we haven't discovered yet. The next few years represent a unique convergence of opportunity and necessity in human history. We have the technological capability to make the measurements that matter, the scientific understanding to interpret the results correctly, and the international framework to coordinate effective responses. Whether we have the institutional wisdom and political will to implement these capabilities effectively remains the critical unknown variable in the equation. Time continues its relentless countdown toward April 13, 2029, carrying with it consequences that extend decades into the future. Every day of delay in mission approvals, every shortcut in observation planning, every failure to coordinate international capabilities increases the probability that we'll face that future less prepared than we could have been. The god of chaos approaches with the precision of celestial mechanics, indifferent to our hopes, fears, or level of preparation. Our response will determine whether this encounter becomes a testament to human foresight and capability, or a reminder of our limitations when confronted with forces beyond our immediate control. Control. The institutional responses we've witnessed so far reveal a troubling pattern of reactive rather than proactive planning that should alarm anyone following this story closely. Space agencies excel at managing routine operations and planned missions, but their track record with rapidly evolving situations exposes significant gaps in crisis management capabilities. Consider how the initial Apophis discovery unfolded in 2004. When preliminary calculations suggested a significant impact probability, the response was scientifically rigorous but operationally chaotic. Researchers worked frantically to gather additional observations while maintaining public silence about the potential threat. This approach worked because more data eventually reduced the impact probability to negligible levels, but it established a dangerous precedent of managing public communication through selective information release. The current situation presents similar communication challenges but with higher stakes and shorter timelines. Agencies must balance scientific honesty about remaining uncertainties against the need to maintain public confidence and political support for expensive observation programs. This balance becomes increasingly difficult to maintain as technical discussions leak into public forums through research papers, conference presentations, and informal scientific networks. The language patterns emerging in official statements reveal this tension clearly. Phrases like continued monitoring to reduce uncertainties and refinement of orbital models serve as bureaucratic euphemisms for acknowledging that fundamental questions remain unanswered. While this careful phrasing serves important purposes in preventing premature panic, it also means policymakers and the public aren't receiving complete information about the true scope of what we don't yet know. The budget allocation processes that determine mission funding operate on cycles that align poorly with the urgent timelines of asteroid encounter preparation. Major space missions require years of planning, international negotiation, and incremental funding commitments that span multiple political administrations. The European Space Agency's Ramses mission faces approval deadlines that leave little margin for delays or complications in the decision-making process. If mission approval is delayed beyond late 2025, the launch window for arriving at Apophis before the Earth flyby closes permanently. This represents a unique observational opportunity that, once lost, cannot be recovered through alternative approaches or future missions. The consequences of this missed opportunity would persist for decades, potentially leaving us blind to changes that occur during the most critical phase of the encounter. The international coordination mechanisms that theoretically exist for planetary defense have never been tested under the pressure of a real evolving threat. The United Nations Office for Outer Space Affairs provides a framework for cooperation, but implementation depends on voluntary participation from member nations operating under different political systems, budget constraints, and strategic priorities. Recent geopolitical tensions have already complicated scientific cooperation in other domains, raising questions about whether effective coordination would be possible if asteroid deflection became necessary. The technological capabilities required for deflection missions are concentrated among a small number of spacefaring nations, creating dependencies that could prove problematic under crisis conditions. The technical challenges facing the proposed observation campaigns extend beyond simple instrument sensitivity to encompass data processing, analysis, and interpretation capabilities that push the boundaries of current computational infrastructure. The volume of high-resolution imaging, thermal mapping, and precise tracking data generated during the flyby period will exceed the processing capacity of individual research institutions. Distributed analysis across multiple international facilities introduces new coordination challenges and potential single points of failure. If key computational resources become unavailable during the critical analysis period, either through technical failures or political complications, the ability to extract meaningful conclusions from the observational data could be severely compromised. The artificial intelligence systems being developed to assist with data analysis offer powerful capabilities, but introduce their own categories of risk that receive insufficient attention in current planning. Machine learning algorithms trained on simulated asteroid encounter data might miss real-world phenomena that weren't included in their training scenarios, potentially overlooking crucial indicators of surface changes or orbital perturbations. The black box nature of advanced neural networks makes it difficult to understand when they might be producing unreliable results or operating outside their validated parameter ranges. Human oversight of AI-assisted analysis requires expertise in both asteroid dynamics and machine learning systems, a combination of skills that exist in very few individuals worldwide. The ground-based observation networks that will provide continuous tracking during the encounter face vulnerabilities that could create gaps in coverage precisely when comprehensive monitoring is most essential. Political instability in regions hosting key observatory facilities, extreme weather events, or equipment failures could disrupt observations during critical phases of the flyby. The growing problem of space debris and satellite congestion around Earth poses additional threats to the precision measurements needed for accurate orbit determination. Radio frequency interference from communication satellites can degrade radar observations, while orbital debris could potentially damage space-based assets contributing to the observation campaign. Solar activity during the encounter period represents another uncontrollable variable that could significantly impact observation quality. Coronal mass ejections and geomagnetic storms can disrupt ionospheric propagation conditions, interfere with satellite communications, and force sensitive instruments into protective modes when maximum sensitivity is required. The meteorological conditions at ground-based facilities during the flyby period will partly determine the quality of optical observations possible from different geographic regions. Cloud cover, atmospheric turbulence, and seasonal weather patterns could limit visibility during the most scientifically valuable phases of the encounter, particularly for facilities in regions with challenging climates. The data transmission and communication infrastructure required to coordinate real-time observations across global networks faces capacity constraints that haven't been fully addressed in current planning. High-resolution imaging and precise tracking data generate information volumes that exceed the bandwidth of existing deep space communication systems. Priority conflicts between different scientific programs competing for limited communication resources could force compromises in data quality or temporal resolution precisely when comprehensive coverage is most critical. The interdependencies between various observation systems create cascading failure modes that haven't been thoroughly analysed or mitigated. The human factors aspects of managing such a complex high-stakes observation campaign deserve greater attention than they've received in technical planning discussions. Researcher fatigue, time zone coordination challenges, and decision-making under pressure could all contribute to errors in data collection, analysis, or interpretation that persist in the scientific record for decades. The institutional memory of lessons learned from previous asteroid encounters remains concentrated among a relatively small number of senior researchers approaching retirement. If this expertise isn't properly transferred to younger scientists before the Apophis encounter, crucial insights about interpreting complex dynamical data could be lost permanently. The policy frameworks for responding to various observational outcomes remain largely theoretical and untested. If measurements reveal higher impact probabilities than currently calculated, the mechanisms for rapidly implementing deflection missions aren't clearly defined or adequately resourced. The time required for international consensus building on expensive response programs could exceed the available window for effective intervention. The financial implications of different response scenarios haven't been thoroughly analysed or prepared for by relevant government agencies. Asteroid deflection missions require substantial international investment, sustained over periods that span multiple political and budget cycles, testing the limits of democratic decision-making processes for managing long-term, probabilistic threats. The legal and regulatory frameworks governing asteroid deflection activities remain underdeveloped despite decades of theoretical discussion. Questions about liability, environmental impact assessment, and international oversight of deflection missions lack clear answers that could prove crucial if rapid implementation becomes necessary. The technological readiness levels of various deflection concepts vary significantly, with some approaches requiring additional years of development and testing before operational deployment becomes feasible. The timing mismatch between when deflection decisions might become necessary and when deflection capabilities could be realistically implemented represents a critical gap in current preparedness. The cascade effects of asteroid deflection activities on other space operations haven't been comprehensively evaluated. Large-scale deflection missions could interfere with satellite operations, space station activities, or other scientific programs in ways that create secondary consequences extending far beyond the immediate deflection objectives. The public communication challenges surrounding evolving risk assessments will require unprecedented sophistication in explaining complex scientific uncertainties without triggering either complacency or panic. The media coverage patterns established during initial encounter reporting will likely persist throughout the observation campaign, potentially distorting public understanding of what the measurements actually reveal. The psychological impacts on both researchers and the general public of living with uncertain, but potentially catastrophic threats deserve consideration in planning communication strategies. Unlike acute emergencies that demand immediate responses, evolving asteroid threats can persist as background concerns for decades, affecting individual decision-making and social priorities in subtle but significant ways. The educational opportunities presented by the Apophis encounter could help build broader public understanding of planetary defense concepts and space science more generally. However, realizing these benefits requires coordinated outreach efforts that compete with other priorities for limited resources and attention. The technological spin-offs from advanced observation and analysis techniques developed for the encounter will likely find applications in other scientific domains, but capturing these benefits requires deliberate technology transfer efforts that aren't automatically included in mission planning processes. The international cooperation precedents established during the Apophis observation campaign will influence how future planetary defense activities are organized and implemented. The success or failure of coordination efforts during this encounter will shape institutional relationships and capabilities for decades to come. The timeline pressures facing all aspects of encounter preparation continue to intensify as 2029 approaches. Every month of delay in mission approvals, observation planning, or international coordination reduces the available time for addressing problems that inevitably emerge during complex technical programs. The compounding effects of these various challenges create risk multipliers that aren't adequately captured in current planning documents or risk assessments. Individual problems that might be manageable in isolation could combine in ways that overwhelm response capabilities if they occur simultaneously during the critical encounter period. The opportunity costs of focusing extensive resources on Apophis observation and analysis include reduced attention to other potentially threatening asteroids that might be discovered during the same timeframe. The concentration of expertise and infrastructure on a single object could create blind spots in broader planetary defense capabilities. The precedent-setting aspects of how the Apophis encounter is managed will influence public expectations, political support, and resource allocation for planetary defense programs extending decades into the future. Success in demonstrating competent management of this challenge could establish sustainable support for ongoing programs, while failures could undermine confidence in institutional capabilities for years to come. The unknown unknowns lurking within our current understanding of asteroid encounter dynamics represent perhaps the greatest source of concern for researchers intimately familiar with the technical challenges involved. History suggests that every close spacecraft encounter with asteroids has revealed surprises that forced revisions to theoretical models and assumptions. The Apophis flyby represents the most extreme test of our predictive capabilities ever attempted in planetary science. Unlike controlled laboratory experiments or routine spacecraft operations, this encounter involves forces, timescales, and physical processes that operate at the limits of our current understanding under conditions that cannot be replicated or repeated. The convergence of all these factors creates a situation where small errors in preparation, measurement, or analysis could have consequences that persist for generations. The responsibility for getting this right falls on institutions and individuals who didn't choose this timeline but must nonetheless rise to meet challenges that will define how well prepared humanity proves to be when confronted with cosmic forces beyond our direct control. The countdown continues with mathematical precision, indifferent to our hopes, concerns, or level of readiness. April 13th, 2029 will arrive regardless of whether we've made the measurements that matter, coordinated the international responses that work, or developed the institutional wisdom required to navigate whatever surprises emerge from humanity's closest encounter with the god of chaos, D of chaos. The orbital mechanics governing this scenario become more disturbing when you examine the mathematical precision required for long-term predictions. Every calculation we make about where Apophis will be in 50 years depends on knowing exactly where it is today, how fast it's moving, and what forces are acting upon it. Sounds simple, it's anything but. Consider the measurement precision required for confident century-scale predictions. If our current position measurements are off by just 1 kilometre, that error propagates through decades of orbital evolution to create positional uncertainties measured in hundreds of thousands of kilometres by the time we reach the late 21st century. We're not talking about minor adjustments to flight paths. We're discussing fundamental uncertainty about which region of the solar system the asteroid will occupy. The force modelling presents even greater challenges. Beyond simple gravitational attraction from the Sun and planets, Apophis experiences the Yarkovsky effect, solar radiation pressure, gravitational perturbations from smaller bodies, and potentially outgassing forces if any volatile materials exist within its structure. Each of these influences operates at different timescales and with different dependencies on physical properties we haven't measured directly. Recent advances in computational modelling have revealed just how sensitive these predictions are to small parameter variations. Change the assumed thermal inertia by 20%, and the long-term trajectory shifts by thousands of kilometres. Adjust the estimated mass by 5%, and the gravitational deflection during the 2029 flyby changes enough to alter which future encounter geometries become possible. This sensitivity analysis exposes a fundamental problem with our current safety assessments. We're building century-scale confidence on measurements that carry inherent uncertainties, then propagating those uncertainties through complex physical processes we've never directly observed for an object like Apophis under the extreme conditions it will experience during close Earth passage. The tidal modelling studies that have emerged over the past 2 years paint increasingly detailed pictures of what might happen to Apophis's internal structure during the encounter. These aren't just academic exercises, they're attempts to quantify whether the asteroid that emerges from Earth's gravitational field will be the same object we've been tracking for decades. Computer simulations of rubble, pile dynamics under tidal stress show that even modest structural changes could redistribute mass in ways that alter the asteroid's moment of inertia. This affects rotation dynamics, which controls thermal behavior, which determines the Yarkovsky acceleration, which governs long-term orbital evolution. Everything connects to everything else in ways that make isolated analysis nearly impossible. The experimental validation of these models relies primarily on laboratory studies of meteorite samples subjected to stress testing. But meteorites represent material that survived atmospheric entry and impact, potentially making them unrepresentative of the bulk composition of asteroids still in space. We're making crucial assumptions about material properties based on samples that may not accurately reflect what we'll encounter. The rotation state uncertainty represents perhaps the most consequential knowledge gap in our current understanding. Ground-based observations suggest Apophis rotates with a period of roughly 30 hours, but light curve analysis from Earth can be ambiguous. A tumbling asteroid with the right geometry can produce brightness variations that mimic simple rotation, leading observers to incorrect conclusions about the object's true dynamical state. If Apophis is actually tumbling rather than rotating simply, every thermal model we've constructed becomes questionable. The Yarkovsky effect depends critically on which parts of the surface face the Sun at specific times during the rotation cycle. For a simply rotating object, this is predictable and modelable. For a tumbling object, it becomes a chaotic system, where small uncertainties grow exponentially over time. The spacecraft missions designed to resolve these ambiguities face technical challenges that push current technology to its limits. OSIRIS-APEX must operate in the harsh radiation environment near the Sun, while potentially dodging debris from surface changes occurring on Apophis during the flyby. The spacecraft's instruments need to function reliably, under conditions they were never designed to encounter. The proposed Ramses mission confronts even more demanding requirements. Observing an asteroid during active tidal deformation requires maintaining precise pointing and communication, while the target object potentially changes shape, rotation, and surface properties in real time. It's like trying to photograph a moving target from a moving platform, while both are experiencing forces that could alter their behavior unpredictably. Data storage and transmission capabilities become critical bottlenecks when you consider the information volumes these missions will generate. High-resolution imaging of surface changes, thermal mapping of temperature variations, and precise tracking of rotation dynamics will produce terabytes of data that must be stored on board, then transmitted back to Earth through communication systems with limited bandwidth. The timing constraints make these challenges even more severe. The most scientifically valuable observations occur during the brief period when tidal forces are strongest, which coincides with when communication with Earth becomes most difficult due to solar interference and spacecraft positioning requirements. Ground-based observation campaigns face their own constellation of technical and logistical hurdles that receive insufficient attention in public discussions. The asteroid will be optimally positioned for observation from only certain geographic regions during critical phases of the encounter. Weather, equipment failures, or political complications at key sites could create gaps in coverage precisely when continuous monitoring is most essential. The international coordination required to maintain global observation coverage involves dozens of facilities operating under different institutional frameworks, technical standards, and funding structures. Achieving true data compatibility and real-time coordination across this diverse network requires years of advanced planning that's still incomplete in many crucial areas. Radio frequency interference from the rapidly expanding constellation of communication satellites poses an emerging threat to the precision radar observations that provide our most detailed information about asteroid rotation and surface properties. The electromagnetic environment around Earth grows more cluttered each year, making it increasingly difficult to detect the faint echoes that reveal crucial physical characteristics. The computational infrastructure required to process and analyze the observational data will strain the resources of even the most advanced research institutions. Real-time orbital determination during the encounter requires massive computational power to integrate complex gravitational dynamics while accounting for measurement uncertainties and various perturbative forces. Machine learning algorithms offer potential solutions for managing these computational demands, but they introduce new categories of risk that aren't fully understood. Neural networks trained on simulated encounter data might miss real-world phenomena that weren't included in their training scenarios, potentially overlooking crucial indicators of unexpected behavior. The human expertise bottleneck represents another critical vulnerability that receives little public attention. The community of researchers with deep experience in asteroid encounter dynamics is relatively small and concentrated at a few institutions worldwide. If key personnel become unavailable during the critical analysis period, essential insights about Apophis's behavior might be missed or misinterpreted. The policy implications of various observational outcomes remain largely unaddressed by current planetary defense frameworks. The United Nations structure for coordinating responses to asteroid threats has never been tested under the pressure of evolving risk assessments based on real-time measurements of a potentially threatening object. What happens if post-flyby observations reveal that impact probabilities are significantly higher than previously calculated? The mechanisms for rapidly implementing deflection missions aren't clearly defined, adequately funded, or politically validated. The time required for international consensus building on expensive response programs could exceed the available window for effective intervention. The financial implications of different response scenarios haven't been thoroughly analysed or prepared for by relevant government agencies. Asteroid deflection missions require sustained international investment over periods that span multiple political and budget cycles, testing the limits of democratic decision-making processes for managing long-term probabilistic threats. The technological readiness levels of various deflection concepts vary dramatically, with some approaches requiring years of additional development before operational deployment becomes feasible. The timing mismatch between when deflection decisions might become necessary and when deflection capabilities could realistically be implemented represents a critical gap in current preparedness. The legal and regulatory frameworks governing asteroid deflection activities remain underdeveloped despite decades of theoretical discussion. Questions about liability, environmental impact assessment, and international oversight of deflection missions lack clear answers that could prove crucial if rapid implementation becomes necessary. The cascade effects of large-scale deflection activities on other space operations haven't been comprehensively evaluated. Major deflection missions could interfere with satellite operations, space station activities, or scientific programs in ways that create secondary consequences, extending far beyond the immediate deflection objectives. Public communication strategies during and after the flyby will require unprecedented sophistication in explaining evolving scientific uncertainties without causing unnecessary alarm or dangerous complacency. The challenge lies in acknowledging genuine risks while maintaining confidence in our scientific capabilities and institutional preparedness. The media coverage patterns established during initial encounter reporting will likely persist throughout the observation campaign, potentially distorting public understanding of what the measurements actually reveal about long-term safety. Correcting misunderstandings and maintaining accurate discourse about complex probabilistic assessments requires coordination between scientific institutions and communication professionals. The psychological impacts on researchers, policymakers, and the general public of living with uncertain but potentially catastrophic threats deserve greater consideration in planning response strategies. Unlike acute emergencies that demand immediate action, evolving asteroid threats can persist as background concerns for decades, affecting resource allocation decisions and social priorities in ways that aren't well understood. The educational opportunities presented by intensive public attention during the Apophis encounter could help build broader understanding of planetary defense concepts and space science more generally. However, realizing these benefits requires coordinated outreach efforts that compete with other priorities for limited resources and expert attention. The international cooperation precedents established during the observation campaign will influence how future planetary defense activities are organized and funded. The success or failure of coordination efforts during this encounter will shape institutional relationships and response capabilities for decades to come, potentially determining whether humanity develops effective defenses against future asteroid threats. The technological spin-offs from advanced observation and analysis techniques developed for the encounter will likely find applications in other scientific domains, but capturing these benefits requires deliberate technology transfer efforts that aren't automatically included in mission planning processes. The opportunity costs of concentrating extensive resources on Apophis observation and analysis include reduced attention to other potentially threatening asteroids that might be discovered during the same timeframe. The focus on a single, well-characterized object could create blind spots in broader sky survey programs designed to identify new threats. The timeline pressures facing all aspects of encounter preparation continue to intensify as we approach the point of no return for mission approvals and observation planning. Every month of delay in critical decisions reduces the available time for addressing the inevitable problems that emerge during complex technical programs operating under unprecedented conditions. The compounding effects of various technical, political, and logistical challenges create risk multipliers that aren't adequately captured in current planning documents. Individual problems that might be manageable in isolation could combine during the encounter period to overwhelm response capabilities in ways that compromise the entire observation campaign. The precedent-setting aspects of how institutional responses to the Apophis encounter are managed will influence public expectations, political support, and resource allocation for planetary defense programs extending decades into the future. Demonstrating competent management of this challenge could establish sustainable support for ongoing programs, while failures could undermine confidence in scientific institutions for years to come. The unknown unknowns lurking within our current understanding represent perhaps the greatest source of concern for researchers intimately familiar with these challenges. Every previous close spacecraft encounter with asteroids has revealed surprises that forced revisions to theoretical models and fundamental assumptions about how these objects behave under stress. The Apophis flyby represents the most extreme test of predictive capabilities ever attempted in planetary science. Unlike controlled experiments or routine operations, this encounter involves forces and timescales operating at the limits of current understanding under conditions that cannot be replicated, repeated, or fully validated in advance. This convergence of factors creates a situation where small errors in preparation, measurement, or analysis could have consequences persisting for generations. The responsibility for managing these challenges falls on institutions and individuals who didn't choose this timeline but must nonetheless demonstrate whether humanity possesses the wisdom and capability to navigate cosmic encounters that could reshape our civilization's future. The mathematics remain unforgiving in their precision. April 13th, 2029 approaches with astronomical certainty, carrying implications that extend far beyond the brief hours of closest approach. Every decision made in the coming months will help determine whether we face that encounter, prepared for whatever surprises emerge, or whether we discover too late that our confidence was built on assumptions that couldn't withstand contact with reality. The god of chaos draws closer, and our window for preparation grows shorter with each passing day. Whether we prove worthy of the challenge remains the critical unknown in an equation where failure isn't measured in embarrassment or career setbacks, but in the potential trajectory of human civilization itself. The mathematical precision required for understanding what happens next defies human intuition. We're not just tracking where Apophis will be in 50 years. We're attempting to predict the behavior of an object that will fundamentally change during those critical hours when Earth's gravity has it in its grip. Every calculation depends on parameters we haven't measured directly, forces we've never observed at this scale, and physical processes that exist at the absolute limits of our current understanding. The cascade of uncertainties begins with something deceptively simple: mass distribution. We estimate Apophis weighs roughly 27 million tons, but that figure represents an educated guess based on size measurements and assumed composition. Without knowing exactly how that mass is distributed throughout the asteroid's interior, we can't predict precisely how tidal forces will affect its structure during the flyby. If the mass is concentrated toward the center, in a dense core surrounded by loosely packed rubble, the tidal response will be completely different than if the material is distributed uniformly. These internal architecture differences determine whether surface landslides occur, whether the rotation state changes, whether structural modifications alter the thermal properties that control long-term orbital evolution. The rotation axis uncertainty compounds this problem exponentially. Current observations suggest Apophis spins around a single stable axis, but detecting complex rotation states from Earth requires resolution that exceeds our current capabilities. If the asteroid is actually wobbling or tumbling, even slightly, the gravitational torque applied during the close approach could nudge it into chaotic rotation that makes thermal modelling nearly impossible. A tumbling Apophis would heat and cool unpredictably as different surfaces face the sun at different times. The Yarkovsky effect, that gentle photon pressure that accumulates over decades, becomes impossible to calculate accurately. Your orbital predictions develop error bars measured in hundreds of thousands of kilometers by the end of this century. The surface composition mystery runs deeper than most people realize. Spectroscopic observations from Earth suggest Apophis belongs to a class of rocky asteroids, but surface properties can vary dramatically across a single object. Some regions might be covered in fine dust that acts like thermal insulation. Other areas might expose solid bedrock that conducts heat efficiently. These variations directly control how different parts of the asteroid respond to solar heating. If the tidal forces during the flyby expose fresh material with different thermal properties, the entire energy balance changes. Dark, newly exposed rock absorbs more sunlight than weathered surfaces. Light-coloured dust reflects more energy than solid stone. Each change alters how the Yarkovsky effect operates in that region, creating a complex patchwork of thermal forces that push the asteroid in slightly different directions. The laboratory experiments that inform our understanding of these processes reveal just how fragile asteroid material can be. Take samples from meteorites that have survived atmospheric entry and impact. Subject them to stress testing that mimics tidal forces. Watch them crumble with shocking ease. These materials have virtually no structural strength beyond what gravity and friction provide. If Apophis consists of similarly weak material held together primarily by its own gravitational attraction, the 2029 flyby represents a stress test, unlike anything the asteroid has experienced in millions of years. The question isn't whether changes will occur. The question is how extensive those changes will be, and whether we'll be able to measure them accurately enough to update our safety assessments. The observational challenges facing researchers in 2029 will be unlike anything attempted before in planetary science. Every telescope, radar system, and spacecraft instrument capable of studying Apophis will be focused on the asteroid during those critical hours. The data volumes will be staggering. The analysis requirements will push computational capabilities to their limits. The margin for error will be essentially zero. Consider what happens if cloud cover obscures critical ground-based observations during the peak of the encounter. Consider what happens if a solar storm disrupts communications precisely when spacecraft are trying to transmit their most important measurements back to Earth. Consider what happens if key personnel become unavailable during the crucial analysis period when time-sensitive decisions about future observations must be made. These aren't hypothetical concerns, they're the kinds of real-world complications that routinely disrupt complex technical operations. The difference is that most scientific programs can recover from temporary setbacks. They can repeat experiments, extend observation campaigns, or wait for better conditions. The Apophis encounter offers no such luxury. Miss the measurements that matter, and you won't get another chance for decades. The international coordination required to maximize the scientific return from this opportunity involves dozens of institutions operating under different political systems, funding structures, and technical standards. Achieving true data compatibility and real-time coordination across this diverse network requires diplomatic finesse that extends far beyond normal scientific collaboration. Recent geopolitical tensions have already complicated international cooperation in other domains. The space programs that possess the most advanced observation capabilities don't always maintain friendly relationships with each other. If political complications interfere with data sharing during the critical analysis period, crucial insights about Apophis's post-flyby behavior might be lost or delayed beyond useful timelines. The artificial intelligence systems being developed to help process the enormous data streams introduce their own categories of risk that receive little public discussion. Machine learning algorithms trained on simulated asteroid encounters might miss real-world phenomena that weren't included in their training scenarios. They could identify spurious patterns in the noise, while overlooking genuine signals that indicate important physical changes. The black box nature of advanced neural networks makes it difficult to understand when they might be operating outside their validated parameter ranges. Human oversight requires expertise in both asteroid dynamics and machine learning systems, a combination of skills that exists in very few researchers worldwide. The financial implications of various post-flyby scenarios haven't been adequately addressed in current planning discussions. If observations reveal higher impact probabilities than currently calculated, implementing deflection missions requires international investment, sustained over multiple budget cycles. Democratic decision-making processes struggle with long-term commitments to expensive programs based on probabilistic rather than certain threats. The legal frameworks governing potential deflection activities remain largely theoretical despite decades of discussion. Questions about liability, environmental impact assessment, and international oversight of deflection missions lack clear answers. If rapid implementation becomes necessary, these unresolved issues could create delays that exceed available response windows. The technological readiness of various deflection concepts varies dramatically. Some approaches require years of additional development and testing before operational deployment becomes feasible. The timing mismatch between when deflection decisions might become necessary and when deflection capabilities could realistically be ready represents a critical gap in preparedness. The cascade effects of major deflection missions on other space activities haven't been thoroughly analysed. Large-scale operations in interplanetary space could interfere with satellite operations, space station activities, or scientific programs in ways that create secondary consequences extending far beyond immediate deflection objectives. The communication challenges during and after the flyby will test institutional capabilities in unprecedented ways. How do you explain to the public that mounting the most intensive asteroid observation campaign in history represents prudent scientific practice rather than acknowledgement of imminent danger? How do you maintain confidence while acknowledging genuine uncertainties about long-term outcomes? The careful language already appearing in agency statements reveals these tensions clearly. Terms like refining orbital models and reducing measurement uncertainties serve as diplomatic euphemisms for acknowledging that fundamental questions remain unanswered. This measured approach prevents premature panic, but also means decision-makers and the public aren't receiving complete information about what's truly at stake. The media coverage patterns established during initial reporting about Apophis will likely persist throughout the encounter period, potentially distorting public understanding of what the measurements actually reveal. Correcting misunderstandings about complex probabilistic assessments requires coordination between scientific institutions and communication professionals operating under intense time pressure. The psychological impacts of living with evolving but uncertain threats deserve consideration in planning response strategies. Unlike acute emergencies that demand immediate action, potential asteroid impacts can persist as background concerns for decades, affecting resource allocation decisions and social priorities in ways that aren't well understood or adequately studied. The educational opportunities presented by intense public attention during the encounter could help build broader understanding of planetary defense concepts and space science more generally. However, realizing these benefits requires coordinated outreach efforts that compete with other priorities for limited expert time and institutional resources. The precedents established during the Apophis observation campaign will influence how future planetary defense activities are organized, funded, and implemented. Success in demonstrating competent management of this challenge could establish sustainable political support for ongoing programs. Failures could undermine confidence in scientific institutions and planetary defense capabilities for years to come. The technological developments driven by encounter preparation will likely find applications extending far beyond asteroid studies. Advanced observation techniques, computational methods, and international coordination mechanisms could benefit other scientific domains. But capturing these spillover benefits requires deliberate technology transfer efforts that aren't automatically included in mission planning processes. The opportunity costs of concentrating extensive resources on Apophis include reduced attention to other potentially threatening asteroids that might be discovered during the same period. Sky survey programs designed to identify new threats compete for the same telescopes, personnel, and funding that encounter observations require. The timeline pressures continue intensifying as critical decision points approach. Mission approval deadlines, observation planning requirements, and international coordination timelines all converge on narrow windows that leave little margin for delays or complications. Every month of postponed decisions reduces available time for addressing inevitable problems that emerge during complex programs. The compounding effects of various challenges create risk multipliers that current planning documents don't adequately capture. Technical problems, political complications, and logistical difficulties that might be manageable individually could combine during the encounter period in ways that overwhelm response capabilities and compromise the entire observation campaign. The unknown variables lurking within current understanding represent perhaps the greatest concern for researchers familiar with these challenges. Every previous spacecraft encounter with asteroids has revealed surprises that forced revisions to theoretical models and basic assumptions about how these objects behave under extreme conditions. The Apophis flyby represents the most demanding test of predictive capabilities ever attempted in planetary science. Unlike controlled laboratory experiments or routine spacecraft operations, this encounter involves forces and timescales that operate at the absolute limits of current knowledge under conditions that cannot be replicated or validated in advance. The convergence of all these factors creates a situation where small errors in preparation, measurement, or interpretation could have consequences that persist for generations. The institutions and individuals responsible for managing these challenges didn't choose this timeline, but they must nonetheless demonstrate whether human civilization possesses the wisdom and technical capability to navigate cosmic encounters that could reshape our future. The mathematical certainty continues its countdown toward April 13th, 2029, indifferent to our hopes, concerns, or level of preparation. Every decision made in the remaining time will help determine whether we face that encounter ready for whatever revelations emerge, or whether we discover too late that our confidence was built on assumptions that couldn't survive contact with the reality of forces beyond our control. The god of chaos approaches with astronomical precision, carrying implications that extend decades beyond those brief hours of closest approach. Our response to this challenge will define not just our scientific capabilities, but our species' readiness to confront the cosmic forces that have shaped planetary evolution throughout the history of the solar system. Time grows short, options narrow, and the margin for error approaches zero. Whether we prove capable of rising to meet this test remains the critical unknown in an equation where the stakes couldn't be higher and the deadline cannot be extended. The universe waits for no one, and April 13th, 2029 will arrive precisely on schedule, regardless of whether we're prepared for what it brings. The gravitational modelling studies that continue emerging from research institutions worldwide paint an increasingly complex picture of what those critical hours might unleash. These aren't merely academic exercises conducted in sterile computer laboratories. They represent desperate attempts to quantify whether the fundamental assumptions underlying 2 decades of safety calculations will survive contact with reality. The latest simulations from the European Space Agency's Advanced Dynamics Laboratory reveal scenarios that should terrify anyone who understands their implications. When researchers model Apophis as a loosely bound collection of rocks and dust, rather than a solid monolithic structure, the tidal forces during closest approach don't just squeeze the asteroid gently, they trigger what can only be described as controlled avalanches across vast sections of its surface. Picture a mountainside covered in loose scree, held in place by nothing more than gravity and friction. Now imagine invisible hands stretching and compressing that entire mountain while it tumbles through space at tremendous velocity. The mathematical models show material flows that could reshape entire hemispheres of the asteroid within hours, exposing subsurface layers that have been hidden from sunlight for millions of years. Each grain of dust that shifts position, each boulder that tumbles to a new resting place, each crack that opens in response to unprecedented stress contributes to a cascade of changes that propagate through every subsequent calculation. The asteroid's center of mass moves, its rotation becomes less predictable, its thermal response to solar heating transforms in ways that make the Yarkovsky effect impossible to model with current precision. The experimental validation supporting these simulations relies on laboratory tests that push the boundaries of what's technically feasible. Researchers have subjected meteorite samples to stress conditions that approximate tidal forces, watching through high-speed cameras as the material responds to forces it was never designed to withstand. The results are both fascinating and deeply unsettling. Under relatively modest stress, samples that appear solid and stable begin developing internal fractures that aren't visible from the surface. The cracks propagate through the material following paths of least resistance, creating networks of weakness that compromise structural integrity in unpredictable ways. When the stress exceeds critical thresholds, failure happens rapidly and catastrophically. If Apophis contains similar structural weaknesses, and there's every reason to believe it does, the 2029 encounter represents a stress test that could fundamentally alter not just its surface appearance, but its internal architecture. We might emerge from the flyby tracking an object that's physically different from the one we've been observing for decades. The rotation state analysis presents another layer of complexity that keeps dynamicists awake at night. Current ground-based observations suggest Apophis spins in a relatively simple manner, but detecting complex tumbling motions from millions of kilometers away requires observational precision that exceeds current capabilities by substantial margins. If the asteroid is already experiencing subtle wobbling or precession that we haven't detected, the gravitational torque applied during Earth passage could amplify these motions into full chaotic tumbling. A tumbling Apophis becomes exponentially harder to model thermally because the sun illumination pattern becomes unpredictable. Different surfaces heat and cool at different times in ways that create thermal thrust vectors pointing in constantly changing directions. The computational challenges of modeling tumbling motion over decades stretch current supercomputing capabilities to their absolute limits. Each small uncertainty in the initial tumbling state propagates through the calculations, creating error bars that grow exponentially with time. By the end of this century, the possible positions form probability clouds, measured in millions of cubic kilometers of space. The spacecraft reconnaissance missions designed to characterize these phenomena face engineering challenges that border on the impossible. OSIRIS Apex must navigate to an asteroid that might be actively changing shape, shedding debris, and rotating in ways that weren't predicted when the mission was originally designed. The spacecraft's instruments need to function reliably, while potentially dodging material ejected from surface landslides. The proposed Ramses mission confronts even more demanding technical requirements. Observing Apophis during the actual flyby means maintaining precise positioning and communication, while the target object experiences rapid changes in gravitational environment, solar illumination, and potentially structural integrity. It's like trying to photograph a building during an earthquake, while riding in a helicopter that's also being buffeted by the same forces. The data storage and transmission bottlenecks become critical when you consider the information volumes these observations will generate. High-resolution imaging of surface changes occurring in real time, thermal mapping of temperature variations across a potentially tumbling object, and precise tracking of rotation dynamics that might be changing chaotically will produce data streams that exceed the capacity of current spacecraft communication systems. The timing constraints make these challenges exponentially more difficult. The most scientifically valuable measurements occur during the brief window when tidal forces reach maximum intensity, which coincides precisely with when solar interference makes communication with Earth most problematic and when spacecraft positioning becomes most challenging. Ground-based observation networks face their own constellation of vulnerabilities that could create catastrophic gaps in coverage during the most critical phases of the encounter. The asteroid will be optimally positioned for detailed study from only certain geographic regions during specific time windows that cannot be extended or repeated. Weather conditions, equipment failures, political instability, or even routine maintenance schedules at key observatory sites could disrupt observations precisely when continuous monitoring becomes most essential for understanding what's happening to the asteroid. The international coordination required to maintain global coverage involves dozens of facilities operating under completely different institutional frameworks and funding structures. The radio frequency interference problem continues worsening as communication satellite constellations expand rapidly around Earth. The electromagnetic environment grows more cluttered each month, making it increasingly difficult to detect the faint radar echoes that provide our most detailed information about asteroid rotation, surface roughness, and internal structure. The computational infrastructure required to process observational data in real time during the encounter will strain resources at even the most advanced research institutions worldwide. Integrating measurements from dozens of different instruments, cross-correlating observations across multiple wavelengths, and extracting meaningful conclusions about physical changes requires computational power that exceeds current capabilities. Artificial intelligence systems offer potential solutions for managing these computational demands, but they introduce new categories of failure modes that aren't well understood or adequately planned for. Machine learning algorithms trained on simulated encounter scenarios might miss real-world phenomena that weren't included in their training datasets, potentially overlooking crucial indicators of unexpected behavior. The human expertise bottleneck represents perhaps the most critical vulnerability in the entire observation campaign. The global community of researchers with deep experience in asteroid encounter dynamics numbers in the dozens rather than hundreds. If key personnel become unavailable during the critical analysis period, either through illness, travel complications, or institutional conflicts, essential insights about Apophis's behavior could be missed entirely. The policy frameworks for responding to various observational outcomes remain largely theoretical and completely untested under real-world pressure. The United Nations mechanisms for coordinating international responses to asteroid threats have never been activated for an actual evolving situation where impact probabilities might be increasing rather than decreasing. What happens if post-flyby measurements reveal that our safety calculations were overly optimistic? The legal, financial, and technical mechanisms for rapidly implementing deflection missions don't exist in any operational sense. The time required for international consensus building on expensive response programs could easily exceed whatever window remains for effective intervention. The deflection technology readiness levels vary dramatically across different conceptual approaches. Some techniques require years of additional development and testing before they could be deployed operationally. Others depend on international cooperation and resource sharing that hasn't been negotiated or agreed upon by relevant government agencies. The cascade effects of large-scale deflection activities on other space operations represent another completely unanalyzed aspect of potential response scenarios. Major deflection missions could interfere with satellite operations, space station activities, and scientific programs in ways that create secondary consequences, extending far beyond the immediate deflection objectives. The financial implications of different response scenarios haven't been thoroughly assessed or prepared for by any government agency with actual budget authority. Asteroid deflection missions require sustained international investment over periods that span multiple political administrations and budget cycles, testing the absolute limits of democratic decision-making processes for managing long-term probabilistic threats. The communication challenges during and after the flyby will require institutional sophistication that has never been demonstrated at the required scale. How do you explain to a global audience that mounting the most intensive asteroid observation campaign in human history represents prudent scientific practice rather than acknowledgement of imminent catastrophic danger? The careful diplomatic language already appearing in official agency statements reveals these tensions with startling clarity. Phrases like continued monitoring to refine orbital parameters and ongoing observations to reduce measurement uncertainties serve as bureaucratic euphemisms for acknowledging that fundamental questions about long-term safety remain completely unanswered. This measured approach serves important purposes in preventing premature public panic, but it also means that policymakers, funding authorities, and the general public aren't receiving accurate information about the true scope of what remains unknown about this encounter and its potential consequences. The media coverage patterns established during initial reporting about the 2029 flyby will likely persist throughout the entire observation campaign, potentially distorting public understanding of what the measurements actually reveal about evolving risk assessments. Correcting misunderstandings about complex probabilistic calculations requires coordination between scientific institutions and communication professionals operating under unprecedented time pressure. The psychological impacts on researchers, government officials, and the general public of living with uncertain but potentially civilization-ending threats deserve much greater consideration in planning institutional response strategies. Unlike acute emergencies that demand immediate decisive action, evolving asteroid threats can persist as background concerns for decades, affecting resource allocation decisions and social priorities in ways that aren't well understood. The educational opportunities presented by intense global attention during the encounter could help build broader public understanding of planetary defense concepts and space science more generally. However, realizing these benefits requires coordinated outreach efforts that compete directly with other institutional priorities for limited expert time and communication resources. The international cooperation precedents established during the Apophis observation campaign will influence how future planetary defense activities are organized, funded, and implemented for decades to come. Success in demonstrating competent management of this unprecedented challenge could establish sustainable political support for ongoing programs. Institutional failures could undermine public confidence in scientific capabilities and planetary defense infrastructure for generations. The technological developments driven by encounter preparation requirements will likely find applications extending far beyond asteroid studies into other scientific and engineering domains. Advanced observation techniques, computational analysis methods, and international coordination mechanisms could benefit numerous other fields. But capturing these spillover benefits requires deliberate technology, transfer efforts that aren't automatically included in current mission planning processes. The opportunity costs of concentrating extensive observational resources on a single, well-characterized object include reduced attention to other potentially threatening asteroids that might be discovered during the same time period. Sky survey programs designed to identify new threats compete directly for the same telescope time, personnel expertise, and funding that encounter observations require. The timeline pressures facing every aspect of encounter preparation continue intensifying as critical decision points approach with mathematical inevitability. Mission approval deadlines, observation campaign planning requirements, and international coordination timelines all converge on narrow windows that leave virtually no margin for delays, complications, or second chances. The compounding effects of various technical, political, and logistical challenges create risk multipliers that current planning documents don't adequately capture or account for. Individual problems that might be manageable in isolation could combine during the encounter period in ways that completely overwhelm institutional response capabilities and compromise the entire global observation campaign. The precedent-setting aspects of how the Apophis encounter gets managed will influence public expectations, political support levels, and resource allocation patterns for planetary defense programs extending decades into the future. Demonstrating institutional competence in managing this challenge could establish sustainable support for ongoing protective programs. Failures in execution could undermine confidence in scientific institutions and planetary defense capabilities for years to come. The unknown variables lurking within our current understanding represent perhaps the greatest source of concern for researchers who are intimately familiar with the technical challenges involved. Every previous close spacecraft encounter with asteroids has revealed significant surprises that forced major revisions to theoretical models and fundamental assumptions about how these objects behave under extreme stress conditions. The Apophis flyby represents the most demanding test of predictive capabilities ever attempted in the history of planetary science. Unlike carefully controlled laboratory experiments or routine spacecraft operations, this encounter involves physical forces and temporal scales that operate at the absolute limits of current scientific understanding under conditions that cannot be replicated, repeated, or fully validated through advanced testing. The convergence of all these factors creates a situation where relatively small errors in institutional preparation, measurement execution, or data interpretation could have consequences that persist and compound for multiple generations. The responsibility for managing these challenges successfully falls on institutions and individuals who didn't choose this timeline, but must nonetheless demonstrate whether human civilization possesses the collective wisdom and technical capability required to navigate cosmic encounters that could fundamentally reshape our species' future trajectory. The mathematical precision of celestial mechanics continues its relentless countdown toward April 13th, 2029, completely indifferent to our hopes, fears, concerns, or current level of institutional preparation. Every decision made during the remaining preparation time will help determine whether we face that encounter adequately prepared for whatever scientific revelations emerge, or whether we discover too late that our confidence was built on assumptions that couldn't survive direct contact with forces operating beyond our immediate control. The god of chaos approaches with astronomical certainty, carrying implications that will extend for decades beyond those brief hours of closest approach. Our institutional response to this unprecedented challenge will define not just our current scientific and technical capabilities, but our species' fundamental readiness to confront the cosmic forces that have shaped planetary evolution throughout the entire history of our solar system. Time grows shorter with each passing day, available options continue narrowing, and the margin for error in every aspect of preparation approaches zero. Whether we prove capable of rising to meet this ultimate test of human foresight and institutional competence remains the critical unknown variable in an equation where the stakes couldn't possibly be higher and the deadline cannot be extended under any circumstances. The universe operates on its own schedule, indifferent to human convenience, and April 13th, 2029 will arrive precisely when orbital mechanics dictates. Regardless of whether we're prepared for whatever revelations it brings, Asians, it regardless of whether we're prepared for whatever revel brings. The mathematical certainty of orbital mechanics has delivered us to a moment where theoretical becomes tangible, where distant becomes immediate, where preparation meets reality in ways that will define our species' relationship with cosmic forces for generations to come. The final preparations now underway across dozens of institutions worldwide represent humanity's most ambitious attempt to peer behind the veil of celestial mechanics and understand what happens when gravity itself becomes a sculptor of worlds. The European Space Agency's Ramses mission approval process reaches its critical juncture in November 2025, less than 12 months from now. The Ministerial Council meeting that will determine funding represents more than a bureaucratic checkpoint. It stands as a pivotal moment where political will either aligns with scientific necessity or fails to grasp the unprecedented nature of what approaches. Without Ramses observing Apophis before the encounter, we lose the baseline measurements that distinguish between normal behavior and fundamental change. We forfeit the opportunity to watch tidal forces work in real time, to document surface modifications as they occur, to measure rotation changes during the hours when Earth's gravity has the asteroid in its grip. The data we fail to collect cannot be recovered through post-encounter analysis or alternative observation strategies. The spacecraft engineering challenges facing both missions push current technology into uncharted territory. OSIRIS-APEX must operate in a radiation environment near the Sun, while potentially navigating through debris fields created by surface changes on Apophis during the flyby period. The mission planners are essentially designing a robotic explorer to study an object that might be actively transforming while under observation. Ramses confronts even more demanding technical requirements if approved for development. The spacecraft must maintain precise positioning and communication, while the target asteroid experiences rapid environmental changes, including gravitational stress, solar illumination variations, and potential structural modifications occurring in real time. The technical complexity resembles attempting to photograph a moving target from a moving platform, while both are subject to forces that could alter their behavior unpredictably. The data transmission bottlenecks become critical limiting factors when considering the information volumes these observations will generate. High-resolution imaging of surface changes, thermal mapping of temperature variations across potentially tumbling surfaces, and precise tracking of rotation dynamics that might be changing chaotically will produce data streams exceeding current spacecraft communication capabilities. The timing constraints compound these technical challenges exponentially. The most scientifically valuable measurements occur during the brief window when tidal forces reach maximum intensity, coinciding precisely with when solar interference makes Earth communication most problematic and spacecraft positioning becomes most challenging due to rapidly changing gravitational fields. Ground-based observation networks preparing for the encounter face their own constellation of vulnerabilities that could create catastrophic coverage gaps during critical measurement phases. Apophis will be optimally positioned for detailed study from specific geographic regions during time windows that cannot be extended, repeated, or substituted through alternative approaches. Weather conditions, equipment failures, political complications, or routine maintenance schedules at key observatory sites could disrupt observations when continuous monitoring becomes most essential for understanding asteroid behavior. The international coordination required involves dozens of facilities operating under different institutional frameworks, funding cycles, and technical standards that have never been synchronized for an operation of this complexity. Radio frequency interference from expanding satellite constellations poses an escalating threat to precision observations. The electromagnetic environment around Earth grows more cluttered monthly, making detection of faint radar echoes increasingly difficult. These echoes provide crucial information about asteroid rotation rates, surface roughness characteristics, and internal structural properties that cannot be obtained through other observational methods. The computational infrastructure required for real-time data processing during the encounter will strain resources at even the most advanced research institutions globally. Integrating measurements from dozens of different instruments, cross-correlating observations across multiple wavelengths, and extracting meaningful conclusions about physical changes requires computational power that approaches current technological limits. Artificial intelligence systems being developed to manage these computational demands introduce failure modes that aren't well understood or adequately planned for in current mission designs. Machine learning algorithms trained on simulated encounter scenarios might miss real-world phenomena absent from their training datasets, potentially overlooking crucial indicators of unexpected asteroid behavior. The human expertise bottleneck represents perhaps the most critical vulnerability in the entire global observation campaign. The community of researchers with deep experience in asteroid encounter dynamics numbers in dozens rather than hundreds worldwide. Key personnel becoming unavailable during critical analysis periods could result in essential insights about Apophis behavior being missed entirely. Policy frameworks for responding to various observational outcomes remain largely theoretical and completely untested under real-world operational pressure. United Nations mechanisms for coordinating international responses to asteroid threats have never been activated for actual evolving situations where impact probabilities might increase rather than decrease based on new measurements. Post-flyby measurements revealing overly optimistic safety calculations would trigger response requirements for which operational mechanisms don't exist. The legal, financial, and technical infrastructure for rapidly implementing deflection missions remains conceptual rather than ready for deployment. International consensus-building timelines for expensive response programs could exceed whatever intervention windows remain available. Deflection technology readiness levels vary dramatically across different conceptual approaches currently under development. Some techniques require years of additional research and testing before operational deployment becomes feasible. Others depend on international cooperation agreements and resource-sharing arrangements that haven't been negotiated by relevant government agencies. The cascade effects of large-scale deflection operations on other space activities represent completely unanalyzed aspects of potential response scenarios. Major deflection missions could interfere with satellite operations, space station activities, and ongoing scientific programs in ways that create secondary consequences, extending far beyond immediate deflection objectives. Financial implications of different response scenarios haven't been assessed or prepared for by government agencies with actual budget authority. Asteroid deflection missions require sustained international investment spanning multiple political administrations and budget cycles, testing absolute limits of democratic decision-making processes for managing long-term probabilistic threats. Communication challenges during and after the flyby will require institutional sophistication never demonstrated at the required scale. Explaining that mounting the most intensive asteroid observation campaign in human history represents prudent scientific practice rather than acknowledgement of imminent catastrophic danger requires messaging precision that balances transparency with public stability. Careful diplomatic language appearing in current agency statements reveals these tensions clearly. Phrases like continued monitoring to refine orbital parameters and ongoing observations to reduce measurement uncertainties serve as bureaucratic euphemisms, acknowledging that fundamental questions about long-term safety remain unanswered. This measured approach prevents premature public alarm but means policymakers, funding authorities, and the general public aren't receiving complete information about the true scope of remaining unknowns regarding this encounter and its potential consequences extending decades into the future. Media coverage patterns established during initial flyby reporting will likely persist throughout the observation campaign, potentially distorting public understanding of what measurements actually reveal about evolving risk assessments. Correcting misunderstandings about complex probabilistic calculations requires coordination between scientific institutions and communication professionals operating under unprecedented time pressure. Psychological impacts on researchers, government officials, and the general public of living with uncertain but potentially civilization-altering threats deserve greater consideration in planning institutional response strategies. Unlike acute emergencies demanding immediate decisive action, evolving asteroid threats persist as background concerns for decades, affecting resource allocation decisions and social priorities in ways that aren't well understood. Educational opportunities presented by intense global attention during the encounter could build broader public understanding of planetary defense concepts and space science generally. However, realizing these benefits requires coordinated outreach efforts competing directly with other institutional priorities for limited expert time and communication resources. International cooperation precedents established during the Apophis observation campaign will influence how future planetary defense activities are organized, funded, and implemented for decades. Success demonstrating competent management of this challenge could establish sustainable political support for ongoing programs. Institutional failures could undermine public confidence in scientific capabilities and planetary defense infrastructure for generations. So where does this leave us as we approach the most consequential asteroid encounter in human history? While the world remains mesmerized by 3I Atlas, that distant interstellar wanderer posing no threat to our survival, the real test of our civilization's maturity approaches from much closer to home. April 13th, 2029 will arrive with mathematical precision, carrying implications that extend far beyond those brief hours when the god of chaos passes within satellite distance of our planet. Whether we prove worthy of this challenge, whether our institutions demonstrate the wisdom and capability required to navigate forces that could reshape our future, remains the critical unknown in an equation where failure isn't measured in career setbacks but in the potential trajectory of human civilization itself. The countdown continues, indifferent to our preparation or lack thereof, and we're rapidly running out of time to prove we're ready.